Hi everyone, welcome back, and we'll continue our story with the history of protein phosphorylation. But before that, I'd like to throw out some numbers, and they're pretty interesting. So think about this: in 7 in 10 proteins in mammalian cells are phosphorylated. How cool is that? In their lifetime, 7 in 10 proteins. I think that's a very high number. You'd also be surprised to know that about 3% of the human genome encodes for protein kinases, and that is around 500 or something, 518 genes. And about 147 genes encode for protein phosphatases. Those are pretty impressive numbers to me, at least. So it's just telling us how important protein phosphorylation and dephosphorylation is for our cells. Now let's get into a little bit of the history. So this whole idea of phosphorylation and dephosphorylation was not just inherent to people as it is to us today. It took its own time in its discovery. So what happened? Well, first of all, there's two people's names that we need to put out here, and those two people, they're a couple, and their names are Carl and Gertie, really bad with names, Corey. So this couple, they said that glycogen phosphorylase, which is an enzyme in the glycogen metabolism pathway, and it basically it catalyzes the addition of a phosphate group from an inorganic phosphate to something else, to an acceptor. So glycogen phosphorylase, they said, existed in two forms, and they refer to these forms as phosphorylase A and phosphorylase B. What they found out that phosphorylase A was physiologically active in the absence of cyclic AMP, and phosphorylase B was only active in the presence of high concentrations of cyclic AMP. So they threw these ideas out, and well, great. But it took another 10 years for the real thing to come up. So Earl Sutherland and Fisher and Crabb, I think, they actually won the Nobel Prize for this. And they said, well, these two forms that we talked about here, this is how they function. So you have your phosphorylase B here, and you have your phosphorylase A here. Phosphorylase B is actually phosphorylated using a protein kinase, okay? And this A was the one that is physiologically active. This is the active form of the enzyme, and you could have a protein phosphatase react in this chemical reaction and dephosphorylate this phosphorylase A form and convert it back into phosphorylase B, which is physiologically inactive. So now it makes sense. So now think about it. Why is it only active when there is cyclic AMP? Because when there is cyclic AMP around, this form can use that phosphate group with the help of a protein kinase and convert to phosphorylase A. Alright? So these guys, they won the Nobel Prize for it, and interestingly enough, Ed Krebs, this is another guy, I think, yes, Ed Krebs, or I don't know if it's the same guy, I'm not too sure, but this guy, he said that this phosphorylase kinase, this enzyme here, this was itself regulated by phosphorylation, so it was only active when it was phosphorylated, and then it would go on phosphorylating phosphorylase B. Quite interesting. And in 1963, Joe Lerner discovered that the rate-limiting enzyme in the synthesis of glycogen, which is glycogen synthase, was regulated by this mechanism as well. So another cool discovery. So is this a biochemical mechanism restricted to a limited area of carbohydrate metabolism? No, proteins known to be phosphorylated now number in the thousands. There's many different processes in the cell that use this phosphorylation, dephosphorylation mechanism to turn off and on switches. Alright, so we'll continue with our next topic, which would be the phosphorylation of proteins occurring on 5 residues in the next video. Thank you.